Alright, so we're going to start by stating the refinement lemma. I've referred to it before, but I didn't state it yet. Here is the precise statement. Given any group G, not necessarily finite, suppose we have two subnormal series. Remember, these are just sequences of pairwise normal subgroups of G. So each one is normal in the next one. Occurs to me I should point out, in case it hasn't ever been obvious, in mathematics, when you see a statement like this really means that you're saying A is normal in B and B is normal in C. So if I separate it, it's clear that we're not actually stating how A and C are related, because we actually know in general the only relationship you can get between A and C from this statement is that A is a subgroup of C. You can't actually prove it's normal. But anyhow, I digress. We have two subnormal series, one of length k, one of length l. Then there exists two other subnormal series, both of the same length, k times l, with the following properties. For all I, gi is equal to g prime sub j for some j. In other words, every group in the first subnormal series appears somewhere in this new one. This is what they mean by being a refinement. You've added new groups, but you still have the old ones. Likewise, the h prime sequence is a refinement of h. For all I, the group hi appears somewhere on this sequence. It's equal to h prime sub j for some j. These two things don't say much because, well, there's nothing about uniqueness here, so you're allowed to repeat groups. I mean, you could always take G and replace it with G as normal in itself. That would be stupid, but there's no rule forbidding it. We're not requiring these to be proper subgroups. And actually, for the purposes of the proof, it turns out, in order to get the proof to work, you need to allow this possibility. So this isn't the meat of the theorem. The meat of the theorem is that you can find two refinements that have this property. And this property says that the quotients of the first refinement are isomorphic to the quotients of the second refinement. So as a person who studies discrete math, I work in an area called combinatorics, and in the study of partial orders, given two chains, you can always ask, is there a common refinement, which would mean some sort of chain that includes both of them. In general, that's not true. These are not common refinements because they're different sequences, but they're almost common refinement. They're common up to this idea that the quotients are the same. So before I prove the refinement lemma, let's actually go back to the second part of the Jordan-Hilder theorem and finish it off. So the second part is that you've got two normal series, subnormal series for your group. We'll call this HM and GK. And not only are they subnormal, they're composition series. Which means that all the quotients are simple groups. Well, by the refinement lemma, we can expand these into bigger subnormal series, supposedly. with this nice bijection, okay, I'm going to use the combinatorics notation that square brackets n stands for the set of positive integers 1 through n. So that we have g prime I plus 1 mod g prime I is isomorphic to h prime phi of I plus 1 mod h prime phi of I. So this is just the refinement lemma, but these are composition series, which means that the quotients are simple, which means in particular that HI is the maximal normal subgroup. In HI plus 1. And similarly with the GIs. GI is a maximal normal subgroup in GI plus 1. So how on earth can you possibly make the sequence any bigger? If you make it bigger by adding in a new group, then one of these wasn't maximal, right? If at some point I had an HI plus 1, and I tried to insert something different that was still somehow normal, then this condition of being a maximal normal subgroup is violated. So that means you must have equality here on one of these two ends. In particular, this sequence is obtained by repeats, as is this one. In particular, it's actually still the same subnormal series. They never actually give these things notation. Let's give it notation. Let's call it script G prime, script H prime. Our math blackboard bold. Math blackboard bold H, math blackboard bold G. Then we see up to repetition. We actually have the same series in both. Moreover, whenever h prime I plus 1 is equal to h prime I, what is this quotient group? Why, it's the trivial group. And so up to this permutation and isomorphisms, that corresponds to a case. I guess it's sigma inverse. Let me think carefully. Where the same thing happens, because we have a bijection. This quotient being trivial means the corresponding quotient with the primes is trivial. What does that tell you? That tells you that the number of times you decided to repeat a group in the second quote-unquote refined sequence that turns out isn't actually really refined is the number of times you decide to repeat groups in this first supposedly refined sequence. And so we see k plus the number of repeats, or number of repetitions, is supposed to give us km, the new length. Similarly, m plus the number of repetitions is also km. We've seen that the number of repetitions in both series is the same number, and so we see that it must be the case. So in principle, we could call this one R and we can call this one S, but we've now just seen that R equals S. So we have K plus R equals M plus S, but since R and S are the same, we can cancel them. And so we now finally see that the length of the two original composition series are the same. Likewise, if we restrict our attention from our bijection, let's look at I such that G prime I plus 1 is not equal to G prime I. Then note that this means that G I plus 1 mod G prime I is not the identity group. By the way our isomorphism works, the same is true here. And so what I'm defining, let's call this A. I'm defining a bijection from A to B to phi of A. And the point I'm trying to get at is this corresponds to entries in the original sequence we started with. And similarly for its image. The point being, this only happens when these two groups are distinct, and the only time that happens is when these two groups are exactly groups in order from the original sequence. Because we obtained our newer sequence apparently by only doing repetition. And similar here. If that seems too hard to swallow, I guess let's just point out by example. With length 3, suppose I had 1, 2, 3, 1, 2, 3. According to my theorem, I'm supposed to extend and get something of length 9. Suppose, for instance, this was one of the approaches, one of the expansions we could have gotten from our proof of the refinement lemma, which I haven't given yet. And suppose that if you went through the proof of the refinement lemma with the H sequence, what you got instead was H1's normal and H1 is normal and H1, normal and H2, normal and H2, H2. The point I was trying to make is that there's a bijection between pairs of quotients down here, and so this pair is going to go somewhere, this pair is going to go somewhere, and the point is wherever it goes it's going to have to be to this pair or to this pair, because those are the only quotients that are non-trivial groups. And whichever one of these two choices you have, you can expand it to, or send it upstairs to give you the bijection on the original sequences. So, for instance, suppose our bijection sent the quotient this way. G2 mod G1 was isomorphic to H2 mod H1. Well, then you have that isomorphism already. Oh no, I mean G2 mod G1 was isomorphic to H3 mod H2. Or more accurately, the way I have it written, you had discovered that G'2 mod G'1 was isomorphic to 3, 4, 5, 6, H'7 mod H'6. But then the point is actually looking at what the groups were in the original sequence tells you what your isomorphism was and allows you to figure out what the actual bijection should be. So in principle, you can always write down what the bijection should be. So really the point I should be trying to highlight is that to get from the refinement lemma to this part of the Jordan-Hilder theorem it's technical and annoying, but the annoying technical part is because you just have to realize you're dealing with repetition and figuring out how to handle that properly. But that is the idea. So the really hard part is actually proving the refinement lemma itself. Alright, so it all comes down to the refinement lemma. Here are my two subnormal series. It turns out the approach I'm going to take is I want to refine both of them, and I'm going to, rather than refer to subscripts as individual numbers, I'm going to create a G prime that has two numbers as the subscript, I and J. Starting with 1, 1, which is normal, 1, 1, which is normal, and G prime 1, 2 is normal, and dot, 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 all the way up to G prime 1, M, which is normal, and G prime 2, 1, which is normal, and G prime 2, 2, so on and so forth, all the way up to finally G prime KM. So the first coordinate represents one of the integers 1 through k. The second coordinate represents one of the integers 1 through m. And so there are km total entries in this sequence, like there should be. And let's see, which ordering is this? This would be second coordinate first. So if the first coordinate, let me think carefully. First coordinate first. So if the first coordinate's larger, it's later in the sequence. If the first coordinates are equal, then you look at the second coordinates. It's a bit more complicated this way, but you'll understand why. It makes the bijection part a lot easier. And G prime ij is going to be defined to be a certain group. Gi plus 1 intersect hj times gi. So what this is doing is it's taking gi and gi plus 1, and inside these two groups, between these two groups, is creating a whole sequence of subgroups, namely gi plus 1 intersect h1 times gi. That's equality there because h1 is the trivial subgroup, so this intersection is trivial, which is normal, and gi plus 1 intersect h2 times gi. I need to prove that fact, by the way, which is normal, and gi plus 1 intersect h3 gi, so on and so forth, until finally get gi plus 1 intersect hm gi. hm is the whole group, so this intersection is just gi plus 1. Since gi is a subgroup of gi plus 1, this resulting product is gi plus 1. So the idea is that you're taking your original sequence, and between any two of these groups, you're inserting this entire sequence of groups. This immediately tells you that this is a refinement, because it does include your original groups this way. Of course, I still need to check that we have the normality condition here, which I'll check in a moment. H prime is defined similarly, only instead it's hi plus 1 intersect hj with hi. Oh, that should be gj. Although it may or may not be easier to follow if I actually do it in a slightly different order. gi intersect hj plus 1. hj. So I keep the j's with the second sequence and the i's with the first sequence. Here I'm taking a group hj and hj plus 1, and I'm inserting a whole sequence of normal subgroups, a subnormal series in between. It's the same idea. So for now, let's assume that these actually form subnormal series. That still needs to be proven. In this case, it's worth pointing out the ordering here is slightly different. You start with H11, then you go to H21, H31, till you get to HK1. Then it's H12, H22, and so on. But the advantage of this approach is that the bijection is now going to be from the set of integers k, ordered pairs k times m, because that's the indexing set I'm using, to itself, and it turns out literally you just take the identity. So in order to prove our result, all we need to show is that we actually have subnormal series from our refinements. In other words, that this group is normal in this group. This was our refinements where we expand the subnormal series coming from the g's i's by doing this weird intersect with the hj's and then multiply by the gi's. And likewise, we need to show that these new H sequence is also a refinement by showing this normality. Remember, this is given by taking the HJs, intersecting with the GIs, and multiplying by the HJs. And lastly, in order to finish the proof, we have to prove this isomorphism of quotient groups. Note here that all the notation for the bijection is now hidden away, because we've decided to refer to our groups. So it's worth pointing out here what's going on is that this is what you would call g prime I plus 1 mod g prime I, and this is what you call h prime sigma I plus 1 modulo h prime sigma I. But of course, because we used ordered pairs, it's a little more complicated than that. That should be actually, what is this? ij plus 1 modulo ij. And then this one would be I plus 1 j modulo ij. One might be confused by why the plus ones are on different coordinates. I mean, the way to really do this, if we wanted to be very, very crazy, is you could define g prime I to be, all right, I don't want to get into it. It's a bit annoying, but there's a way to get ordered pairs down into one number. And rather than explain the general bijection, it's easy to explain it by example. Suppose your ordered pairs were a 2 by 3. There's actually two ways. One would be to read row-wise, and the other approach would be read column first. And so one of these sequences would correspond to this approach, and the other sequence would correspond to that approach. And so the plus 1 in one approach corresponds to going to the next row, and in the other direction, adding 1 corresponds to going to the next column. And that's the reason why it looks kind of like this. But the point is there's a bijection between these two series such that these consecutive entries look like this. And so I see by using the ordered pairs, it's slightly more confusing, but at least we're able to get down to this group a lot easier. So then you have to wonder, why are these two groups? We need to prove these quotient groups are isomorphic. That part is easy. Why? Because that's the butterfly lemma. Why? Because Hj is normal in Hj plus 1, and Gi is normal in Gi plus 1. And I stated the butterfly lemma with these groups on the left, but it's still true with the groups on the right. And so there's our application of the butterfly lemma to this crucial step. It tells you that the quotient groups in each of the refined series, normal series, are isomorphic. Know what else it tells you? Or for this isomorphism to be true, it's automatically the case that these are groups, which means that this group must be normal in that group. Oh look, that automatically gives us for free the other two things we needed to check. So the three remaining things we needed to check all follow for free from the butterfly lemma. And this is a sign of an older area of mathematics, by the way, where some theorem ends up being proven as a consequence of some lemma that's a consequence of some other lemma. The original proof of the Jordan-Hilder theorem, whatever it might have been, probably was more complicated. So I apologize if this is a little messy. The resources I had looked at gloss over all these kinds of details a lot more quickly and just jump straight to, well, you refine it this way. But I attempted to make it a little more explicit, but in the end, it's still trying to make it completely rigorous is overly technical, I think, and very detailed, when really the idea is that you're taking each pairs of entries in the sequence and refining them by doing this construction. And then the fact that you get this nice bijection between the two refinements, such that the quotients are isomorphic, is really just the butterfly lemma. So there you have it, a proof of a theorem that the book says is simple, or not too complicated. I think I'm going to go ahead and disagree with the book. Or at least this approach to proving the Jordan-Hilder theorem is relatively complicated. And the exercises in that chapter also try to give you a way to prove it, and I find the approach given by the exercises is about just as complicated.